All right, so next week we have an exam on Monday is our big thing, or not Monday, Wednesday. Exam on Wednesday. That's our big thing, and then Wednesday. And then on Monday we'll have a review in class. So bring your questions. And then I have office hours today. Office hours today, 1:15 to 2:15. If you can't make that and you have questions or things, please reach out to me over the weekend. I'll try to answer them by email, and we can get together by Google Meet if necessary. Questions on stuff we're doing with class? Okay, that exam is going to be on everything since the last exam up to the end of titrations. All right, so things we talk about today. So then I wanted to talk today about what's going on with this titration curve. These are things we talked about in the last, I talked about in my video, okay, which I'm sure you guys have watched. But we look at this now. I just pulled this off the internet, and the title's there. But how would I know that this? If it didn't tell me in the title that it was a titration of weak base with an acid, how would I know? The pH. What about the pH? It starts high and it goes low, right? I'm adding acid, so my pH is dropping, okay? If I was adding base, my pH would be going up. Yes?
How would you know, like, it's a weak base versus a strong base? Like, I know, like, the higher you get, the stronger, but, like, it's kind of like in the middle.
You wouldn't really need to know that. This part of the curve is going to look a little different, but don't worry about it. So a strong acid and base is going to kind of be more straighter. That makes sense? Anyway, so you don't need to be, you need to be able to tell whether it's an acid with a base or a base with an acid. You don't need to be able to tell whether your titration is always going to be, you're always going to be titrating in a strong acid or a strong base. Okay, whatever you're adding is going to be strong. But whether what you're measuring is strong or weak, you don't need to be able to tell that. You just need to know if it's an acid or a base. Let's actually talk about that. So in terms of titrations, the point of a titration is to figure out how much stuff there is. So titrations are used okay. So in other words, more specifically in chemical terms, we're looking for a concentration or a mass. Okay, or it could be moles, but but let's do concentration or mass in terms of what our stuff is. When you do titrations, you often use an indicator. So an indicator is something that tells you when the reaction is complete. So down here, you're titrating a weak base with a strong acid. It would be when all the weak base have reacted. Okay? That's how we know. And often, that indicator is something that changes color. So Dr. Livingston told me you haven't done phenolphthalein yet. That's the one, maybe you did it in high school. It's the one that it's colorless and then it turns pink when the solution gets basic. I think you did in lab. She hadn't emailed me by the time I did my video. You did, it was bromo something blue. One of the bromo what? It was a little bit different. I'm used to a different bromo. It's bromo something blue is what it was. And what it did was it changed from yellow to blue depending on which way you were going, right? I think blue was basic. I don't know for sure. I'm not familiar with that dye, and I can't remember. I knew it when I did my lecture, but I actually told you the wrong direction because I think she had you coming titrating a base with an acid.
Yeah.
Does that sound right? Okay, it turned yellow. Okay, great. Yeah, HCl is the acid, so great. Okay, so let's talk about the parts of this curve. Sometimes though, what you won't use an indicator, we've got these pH probes. You would take a pH probe and you'd measure the pH, and then you'd look for where you have this big break here, right? Okay, so this is not, they just took 4 points. We're just looking at 4 points that are interesting here. What's interesting about number 3? The equivalence point, which means what? Okay, so I'm hearing lots of people telling me the right answers. Nobody's super loud over anybody else, for the most part. You might be loud, but but the equivalence point, that's when everything's reacted. Okay, when all your unknown is reacted. And when I say unknown, I don't mean you don't know what it is. Did you have a question?
I was gonna say, you probably turn the lights on, because it's kind of hard to see.
Oh, I'm happy to turn that light on. Yeah.
I'm happy to close the doors and see if it helps with the sound, but it won't.
Okay, so that's when everything's reacted. So all your bases reacted, or if this was a reaction of an acid with a base, all the acid is reacted. Okay, and when that happens, we see a big quick change in pH. How about this one? This one's really useful too. It's the half equivalence point, and it tells us what?
The concentration of the conjugate base is equal to the acid, and it's where the pH is equal to.
Right, so this is where it's the half equivalence point, and at the half equivalence point, so we'll call it the half equivalence point. And it's where the concentration of your base is equal to the concentration of your acid. Okay? It's where half of this is where everything's reactive, so that's where half of it's reacted. So at the point where half of your, in this case, base is reactive, then half of it's turned, the other half is turned to acid, right? And so this is actually fun. You may just have to take my word for it. I'm not going to do the math for it, but I'm pretty sure that, you know, we have our Henderson-Hasselbalch law, right? Well, I could do that for a base reaction as well. I derived the Henderson-Hasselbalch in class. I haven't actually derived it for the base, but I bet you it's this. The only thing I'm unsure about is whether the acid goes on top or the acid goes on bottom. I'm pretty sure I've got this correct, okay? Or not PKB, okay, like that. Okay, so we do it for the base reaction, but it doesn't even matter for what I want to say right now, what's on top or what's on bottom, because if they're equal, right, if they're equal there, what does that mean? That means that whatever this over this is 1. What's the log of 1? 0. Okay, so when the pH of when these are equal at the half equivalence point, the pK is equal to pKb. So what that means, I can read, or the pH is equal to pKb. That means I can read the pKb right off this graph. What do you think it is? Don't say it. Everybody take 15 seconds and come up what you think it is.
Can I say it after 15 seconds?
Hmm?
Can I say it after 15 seconds?
Mm-hmm. Only if you say it really loud.
Yeah, I don't trust myself. Okay.
All right.
No, wait a minute. Hold on. Hold on.
Yeah.
It looks like it's around 9.
Yeah, around 9 sounds about right. I think I called around 9.2, but you know, this is 8, that's 10, right? It's 9 would be about here. It looks like it's a little higher than 9 to me. I'm going to call it 9.2, okay? But 9 is fine. And to do significant figures correctly, I would call it, I'm going to call the PKB is equal to then 9.2. And this is one significant figure when we go on and do our calculations, because that ends being an exponent.
That estimation
Yeah.
do the 0.0 or the 0.5.
I don't feel like I can estimate any better than 9.2.
No, you only estimate one decimal place past what you're given generally, don't you?
You only estimate, so the question, I'm getting some questions about what these significant figures mean. The last number is the one you're not sure of.
Right.
So I'm saying 9.2 because it might be 9, I can't tell, it's a big dot, a small graph. I can't tell whether it's 9.2 or 9.1 or 9.3, okay? Or even less accuracy than that. And I just pulled this off the internet, I don't know what it is. I don't even know what the base is, okay? So I'm gonna just make stuff up. But, all right, so that's what that is. So what we could do is we can make up a problem using this. All right, so let's go ahead and do that. So let's say that we've got whatever our base is. Okay, we'll just call it A minus. Our mystery base only has one hydroxide per molecule. So it's a monohydroxide. We don't really have like we have monoprotic. We don't really have a good term for that. But our mystery base has only one hydroxide per molecule. It reacts with 0.57 molar hydrochloric acid. Okay. You have, let's say we have 30.0 milliliters of the base to start. What's the concentration of the base? Did I miss something? Well, we do need the amount of HCl. Where do we get it from? The graph.
Oh, I didn't realize.
But great question. So yes, I'm tying this graph to this problem. So we're going to get the amount of HCl is right here. It's how much it's needed to fully react with our base. And so we're going to need to, in this problem, we're going to need to actually work in liters. This problem is going to be a volume of acid. We're going to go to moles of acid. Then we're going to go to moles of base. And then we're going to go to molarity of base. Okay? We're not going to do that. I agree with you, and you can do that. Okay, but what we're going to do is I want to convert those volumes to liters, because if I don't actually need to here, but if I always convert to liters, I'm always safe. All right, so we're going to convert to liters here. So let's go ahead and take this milliliters here, and we're going to convert it to liters separately because we're just going to plop it in our equation later. 30.0 milliliters. And if I have 1,000 milliliters, that's going to give me 1 liter. If I go ahead and pull that out, that's going to be 0.030 liters. Okay? So like Taryn said, we actually don't need to do it because we have milliliters and milliliters and they cancel. And if what I just said didn't make absolute sense to you right off the bat, just always convert to liters. There's some shortcuts you can take, but all right. So then we've got our volume. So our volume of acid is, what was the volume for the equivalence point up here? 20 milliliters, right? So we'll do our conversion here in the dimensional analysis. So I've got 20 milliliters of acid, and if I have 1,000 milliliters of acid, that's going to give me 1 liter of acid. Now, if you're going to do these conversions, you can do them in your head, and that's fine, but make sure you write down what you did on your paper. What I recommend, though, is if you don't always get these right when you do them in your head, always do the dimensional analysis. It tells you whether you should be dividing or multiplying. It's really useful, okay? So by doing this, I'm like super sleep deprived right now, and by doing this, this will help me not make as many mistakes when I'm sleep deprived. And then you guys will pick up the ones after that. But so those two are going to cancel. Now I'm in liters of acid. If I want to go to moles of acid, I'm going to use the molarity here. Now when you see a molarity, that's the same as saying 0.57 moles is equal to 1 liter. So how would I put that into this equation right here? What goes next to my dimensional analysis? Right. 1 liter of acid goes on the bottom because my units are going to cancel, right? And then I get 0.57 moles of acid on the top. All right, and now I need to go to moles of base. Well, I said it was a monoprotic base, right? So it was XOH, whatever that is, plus HCl is going to go to make water and XCl, right? So 1 mole of base reacts with how many moles of acid? 1. So it's a 1-to-1. So we're going to say 1 mole of acid is going to react with 1 mole of base. Moles of acid cancels moles of acid. And I'm going to extend this 1 more here. So I could pop my moles out, and then I could calculate my molarity, right? Because remember, molarity is equal to moles divided by liters. Or I could just stick my liters here, and then I'd have moles of B over, if I have my liters of base, I'd have moles of base over liters of base, right? Okay. And so here I had this many liters of base. It's asking what the original concentration of base was. So 0.030 liters of base. And so now I can put everything in my calculator. 20 times 0.75 divided by 1,000 divided by 0.03. And I get 0.38. Molar, whatever our base is, 8XOH. Other people get that? Good. Questions on that problem, how we do that? Yes?
So when you have the moles of acid over the liters of acid, is that still like you're using the molarity equation, or like can you just walk me through how?
If I have the moles of acid divided by the liters of acid, is it still what I just did there?
Yeah, so because you're taking the molarity of HCl and you're just
Right.
making it moles.
You mean HCl or the base at the end?
HCl.
You're asking this thing right here?
Yeah.
Okay, great. Yeah, so that's, so my molarity for HCl, right, it was equal to 0.57 moles per liter, right? Do you agree that that's 0.5 moles? If I do 0.57 moles over 1 liter, that I get the same number? And then, but that also you could say that that also says that if I have well, let's see, let's do it like this. If I have 1 liter of HCl contains 0.57 moles. I'm just breaking it up, and then I feel like this is easier to think about in terms of how it fits in. But I don't know, you guys can tell me that I'm just confusing you and wasting time when I do that. Okay? Happy to receive feedback on that. Okay. All right, so we've got that. We solved for what our concentration of base was. Let's say instead, so we figured out what our pKb is, right? Let's do the problem. So I could go up to this and I could figure out what my pH was at the equivalence point, right? It's about 5-ish, 5 maybe, something like that. Okay, and we can also solve for this problem if we didn't have the graph. If we have the graph, we can just read it off of it. We also can solve for what the pH is going to be at the equivalence point. And I want to talk about how we would do that. All right, so this is something we're going to take our reaction, we're going to send it to completion, and then we're going to have it come back. So you see that if we, we're going to take those, what were our amounts above? It was 20, we're going to take the amounts from above. I'm just going to rephrase the question. If 20, let's make it two significant, 20 milliliters of 0. Well, let's say 0.3 molar HCl, no, that's not HCl, XOH reacts with, what was it? It was HCl, right? It was, oh, sorry, this was 30. If 30 milliliters of our base reacts with 20 milliliters of 0.57 molar HCl, what is the pH? And let me add the equivalence point. So if this much reacts, that much base reacts with that much acid to reach at the equivalence point, what is the pH? All right, and so the point here is what we want to do is this is a weak base, right? What that means is we're going to completely react with the acid, but then some of that base, some of the weak base is going to go and take it back, if that makes sense. Okay? So I've written it as XOH, and that's probably not good at this point, because we know OH is well, actually it could be a weak base, and that it could be not. Some of those things aren't very soluble, but I'm going to change it to A, so we can do an A minus. I like that better. All right, so let's go ahead and look at that reaction then. And what we're going to do here is, for this, we need to do one of those fire tables. All right, maybe it's an ice table. We're going to write it out. So I start out and I'm going to be at equilibrium, right? I've got my base can react with water to make the conjugate acid, okay, plus OH. Is that what I want? No, I'm going to have all acid, right? I've made all acid at the equivalence point. Let's turn that around, right? Because all of the XA is going to react with the acid. So it's going to be all HA, right? And then that's going to dissociate to give us H plus plus A minus. You guys with me? I kind of changed my mind there in the way I wanted to do it. But this will get me more directly to my pH. So what concentration or what number of moles, we could say, how much of this is there? All right, well, it doesn't matter. The only thing that matters is that if we're going to do concentrations, that what's our volume here? So all these both fully reacted. I mixed them together to fully react. What's my final volume? It's a little tricky. 50 milliliters, right? I poured two things together, so the volume is both of them added up, right? So let's go ahead and figure out how many moles we have. So I know that molarity is equal to moles times liters, okay? And then I know that, well, sorry, molarity is equal to moles over liters. All right, and what that means, I can take liters times both sides and say molarity times liters is equal to moles, right? And we figured this out. I'm going to use this one since we actually figured that number out, right? We decided that 0.38 molar times we figured out that that's that many liters, right? Earlier. And so I can multiply the two of those together. 0.38 times 0.03 gives me 0.0114 moles. And that's going to be the same as this number of moles. If you do that one, you're going to get the same number out to whatever number of significant figures we're doing here. Okay, and so that's how many moles I have, and what volume is that in? Again, 50 milliliters, right. So we've got 0.0114 moles. Remember that that's your thing for molarity, and that's going to be divided by 0.050 liters. I turned 50 milliliters into liters in my head, but you should, unless you're always, you're welcome to do that sort of thing, but unless you're always getting the right answer, you should do dimensional analysis, okay? Yeah.
So if you're saying that something is 0.38 molar, is that not saying that something is 0.38 moles per liter?
Yes.
So why would you multiply it times 0.030? Why wouldn't you multiply it times 1?
So this is because I don't have a liter of it going in. I had 30 milliliters, I dumped it. I had 20 milliliters, I dumped it, right?
Got it, okay.
Good question. Other questions? Okay, so then let's go ahead and get this into molarity, and then we can finally fill out our table. And this is going to be a nice table. So I'm going to divide that by 0.05, and I get 0.228 moles. Okay, so I start with 0.2 molar. Molar, that's really important. Okay, 0.228 molar. I start with, we're going to say I start with 0 H plus, I start with 0 A minus. What's going to happen here? Am I going to add X or subtract X? Subtract X, because I got to move towards the zeros, right? So plus X, and this ends up being 0.228 molar minus X. This ends up being X, and this ends up being X. Okay? So now I want to see if I can apply that simplifying approximation, right? And to do that, I need to know what's the Ka for this. Well, I could use my graph to estimate what the Ka is, right? Not really, but I can get the information I need to, right? We estimated the KB at, what was it, 9.2? All right, and hopefully you remember, but even if you don't, you could look at the top of your test. Remember that 14 is equal to the Ka plus the Kb, right? And we said this was 9.2 plus the Ka is equal to 14. And so I just need to subtract from 14 9.2, and I'm going to get 4.8. Whoops. There we go. So Ka is equal to 4.8. Questions? Am I moving too fast? Okay, I'm skipping a couple steps of algebra here. All right, and then I need to put that in. If I'm going to do an equilibrium expression, I need to have the Ka, not the pKa, right? So remember that your pKa is equal to the negative log of your Ka. So that's equal to the negative log of 4.8, which, well, let's put it right here, is equal to that. So I'm going to go ahead and take the log of that. That can't be right. No, I'm sorry. I put it in the wrong spot, right? My pKa goes here, right? Is equal to my negative log of my Ka. And so to solve this, I need to do that, right? And so now I can take that 4.8. What I need to do actually though, before I raise things to the 10, I need to move this plus over. So multiply both sides by -1. And so I'm going to do 4.8, make it negative, raise it to the 10, and then I get that my Ka is equal to 1.2. So this is actually only one significant figure here. I'm going to do it correctly. Remember, you might be afraid to use just one significant figure because that's one of those danger things. If you make it one significant figure and it's 2, I'm going to mark it off because you add so much rounding error by doing it. So feel free to not round it for safety. But this is just going to be one significant figure, and that's going to be times 2 to the negative 5th. Okay?
What should the 14 equal?
What should the 14 equal?
Where it's like 14 is K.
Ka plus 9.2. So Ka is going to be 4.8.
Oh, and then what is the PK?
What is the pKa? Oh, it's a pKa. I'm sorry. pK.
Oh,
Which is probably part of why I had an issue, right?
so it's PK.
Yep, I copied my formula wrong from the top of my test. Everybody catch that? 14 is not equal to pK that. If you actually wanted to work with Ka's, it's actually 1 times 10 to the negative 14 is equal to the Ka times the Kb. Okay. Questions on that? Because I clearly messed it up, did a whole bunch of steps. It messed me up later. All right. So there's our Ka. So now we can solve the problem, except we want a really quick check and see whether we can do our simplifying of assumption. I'm going to remember 2 times 10 to the negative 5th. I'll just rewrite it here. All right. And so remember for our simplifying assumption that if we take our concentration of our acid and we divide it by our Ka, we want that to be greater than 400, right? And so 0.228 divided by 2e, and I get for that, that's the number I get out. So that is greater than or equal to 400. So I can make my simplifying assumption and get rid of that. Questions?
Do you what's the top again from that one? The top.
What is this thing? That's this.
Oh, yeah.
It's the concentration of my acid. Good question. All right, so I can get rid of that. So now I'm finally ready to solve this. I have my Ka is 2 times 10 to the, let's actually just write it out generally. So I've got my Ka is going to be equal to my products over reactants. My products are H plus and A minus. And that's going to be over my HA like that. If I rewrite it, I'm going to have X on the top and X on the bottom. And then I have a 0.229 molar on the bottom, 228 I think it is, on the bottom. And this is 2 times 10 to the negative 5th. Okay? So then what I can do is multiply. I can multiply by this by both sides to get it out of there, right? So 2e to the negative 5th times 0.228. That's 2, 3, 4, 5, 6. So I've got 4.56 times 10 to the 6. Yeah, times 10 to the negative 6 is equal to x squared. All right, and then I can take the square root of that, and I get 0.002. 1 times, well, is equal to x. That's my concentrate, is equal to x. Somebody else get something different? Okay. And that's equal to my H plus concentration. Okay. feel like I got the same answer last time and I didn't like it. And then we can figure out our pH is going to be equal to our negative log of our H plus concentration. Okay. 0.0021. I'm going to take the log of that. And we get a pH of 2.7. Yes?
Are you okay if we keep all of the decimal? Like, I got a slightly different answer, but it was a rounding thing, because I keep all my
All your
decimals
decimal places until the end. That's fine.
Okay.
It's fine if you keep them all to the end. You should keep a fair number. I may be cutting it down a little bit. But yes, that's the pH we get, which doesn't really match the graph up above, which bothered me. It still bothers me, but we did work the problem correctly.
And also, why did you choose to do the Ka because it's easier because we were finding pH? Because technically we have a strong acid but a weak base, not a.
We're not,
If you had
right,
done
right.
it with the Kb and then had done an ice table with like the weak base and then just subtracted it from 14, leave out at that point.
Right, so this is a really good question. Why did I do the acid, okay, instead of the base? So our original reaction was we had, I'm going to go call it XA for this is my weak base, right? The X is like some counter ion, this is sodium, let's say. But I've got XA plus HNO3, or it was Cl, right?
Yeah.
HCl, and that's going to go ahead, actually it's a strong acid, so it's going to completely react, and it's going to give me water, okay, plus, well, it's not necessarily going to give me water, if it's just an A, right? It's going to give me, let's say, HA plus XC, now, right?
Mhm.
Because this is a base, if this base here is acetate ion,
Mhm.
right, it's not going to give me that. Does that make sense? It's not hydroxide, so I'm not going to get water out of that. You okay so far? Everybody else okay? Any questions? All right, so this, we go to equivalence point, right? Go to equivalence point. All that reacts, right? Because we're titrating in the HCl until we hit an equivalence point. All that reacts, and we end up with all this. And now what we want to think about is how much, so we have 0 and 0, right, where this would be H, we're thinking about this as H plus now, 0 and 0, and then this is going to react back. So it has to be, we have to be working off the acid. It's whatever you go to all of. If it was a weak acid, right, if it's a weak acid, not a very, very weak acid, we're going to be going to a weak base as well.
Okay.
So our strong acids have very, very weak conjugate bases. And so you can't really, they don't react back in solution at all. And our strongest bases have very, very weak acids. But outside of that, if you have a weak acid or a base in the middle, the conjugate is also weak.
Okay.
Does that help?
Yes, and even though it's a conjugate acid, because it's the acid, you're gonna use your HA. Because it's going backwards, it's just a solution, right?
I'm using the HA because that's what I end up with all of at the equivalence point before I figure out that small bit that I get back.
Got it, okay.
Okay, so if instead this had been a reaction where I'd had an HA reacting with a strong base, so we'll call it sodium hydroxide, okay? In this case, actually, I will be able to make water, okay? Plus, I'm going to make A minus. If this was a titration of this acid with the strong base, then at the end of that titration, I'd end up with that's all I'd have. And so then the reaction I would consider for my ice table, I'd consider it coming back this way.
Got it.
Does that make sense?
It would be your KB, right? It would be like your A minus.
Here I would be using the KB, yes.
Would it be A minus plus H plus is maybe
I mean, I would do A minus plus water. It grabs a proton off of water to make HA plus hydroxide.
Got it, okay.
Make sense?
Mm-hmm.
Other questions? That was a good question. Okay. We have, I guess we only have 6 minutes left here. What else? You guys have anything else you'd like me to do? I'm going to do something. I'm going to use 6 minutes. You're not getting them back. Is there anything that you would like me to do? You'd like to see? Yes.
On the graph, was the arrow like pointing at the wrong thing, or was it supposed to be at that?
So way back here. Which thing?
That PKB was 9.2.
No, that's correct. This is a PKB right here.
Wait, why is it at 1 and not 2?
Oh, that's what you mean. It is at 2.
Oh,
So the PKB is, if I draw as straight a line as I can over to there, that's how I'm reading what the PKB is. That's a good, thank you for pointing that out. Yes,
Did we find like what number 4 was?
we did not.
Oh.
And in terms of finding what number 4 is here, so this is a titration of a weak base with a strong acid. So this would be an over titration. So we have half as much acid. Let's really quickly do that if we can, okay? Because that's an important thing. I actually did it with the other class. So now if we're doing this, I had this thing, right? And what I want to make is, I want 1.5 times as much of that acid. All right, so, well, that's easy. I'm going to make 30 milliliters of it. You guys agree that that's 30 milliliters is 1.5 times 20. Okay, and so now we have this, and it's not to reach the equivalence point. We're just going to say, what is the pH? So if 30 milliliters reacts with 30 milliliters at those concentrations, what is the pH? So now we need to figure out how many moles of everything we have, okay? Because things react in moles. Actually, molarity would work here because we have equal volumes, but let's pretend that's not the case. Remember that what we can do is we can take that molarity is equal to moles divided by liters, and so that means if I take liters times both sides, that moles, is equal to molarity times liters. So I can take 0.030, I'm going to just do these in my head in terms of the liter conversion, times 0.38 molar XA is equal to whatever amount of XA I have. And then over here, I'm going to have 0.030 liters times 0.57 molar HCl. Put both of those in my calculator. 0.03 times 0.38 equals 0.0114, and that's moles. And 0.03 times 0.57, that's going to be 0.0171 moles. Okay, and that's how much, this is how much HCl I have, and that's how much XA I have. So let's just rewrite those. 0.0, actually let's not rewrite those, let's set up one of these fire tables. It's going to be a fire table? Yes, it's going to be a fire table. Okay, so we're going to set up a fire table for this. So I have XA is going to react with HCl. Okay, HCl is a strong acid, so we're going to react all the way over to make A minus plus, what else? We got C, we're just going to do Cl minus over here. Okay.
Could you just divide by 60 milliliters to get molarity of each?
And then do it in molar?
Yeah.
We could. We'll divide in a minute. So we can do that when we want for that, but yes.
You end up doing that anyway, right?
You do. Here we'd have to divide all of them by 60. Instead, we're just going to divide the answer by 60.
Okay.
So it'll be less dividing, in my opinion, but it doesn't, you can do it either way. So here we have, so remember, we've got this fire table that goes fire, our first reactant end. Okay, and so we start out with, for XA, we decided we have 0.0114 moles. For HCl, we've got this is moles, 0.0171 moles, and we have 0 of that, right? We're going to have, when we do these fire tables, we go with the smaller one, right? All of this reacts, all this can't react because there's not enough of this to react with it. So all of the first one is going to react. We have minus 0.0114 moles of this goes away, give us 0 down here. And then this is going to be, we're going to subtract that much here as well. And over here, that's going to give us plus 0.0114 moles. Okay, if I carry this down, all my XA reacted, my HCl, how much do I have left? Does anybody figure that out? 0.57, was that it? Okay. Moles. 2 zeros. Bear with me for a minute here, okay? So we're going to do this with 0.0114 moles. That's HCl, it's a strong acid. It fully dissociates, right, to make H plus Cl minus. It fully dissociates there. And so, and it fully, this is supposed to be HA over here, right? That's supposed to be HA. This can't react all of that. I've got this left. I have none of this left. So no more of this. There's no more of that to react with it. So that's my H plus concentration, right? We had 60 milliliters total. So my H plus concentration is going to be 0.0057 moles divided by 0.060 liters, right? Okay, and then I can calculate the pH from that. But I've got excess strong acid at the end, so I'm going to calculate it based on how much of this there is. I don't do any back sort of stuff. Right? I'll let you go with that, and I'll finish the calculation quick for the notes.